We ended the last film with this diagram describing all the forms of acceptability required for a solution to be achievable to deal with climate change. And you can see immediately that the dream solution, the ideal, would be if we could find a new source of energy, possibly with some negative emissions technologies added onto it, that could be delivered without the public finding out. That would be, if we could afford to invest in it, it would meet our existing models of growth based on innovation and investment. It would be hidden from the public so they wouldn't need to change their behaviours. It would be technologically exciting. It would be politically achievable. And it would be very easy. So almost all discussion so far has looked for a solution in that form. We're going to have to analyse whether that is realistic or not. Here is the pie chart of the world's emissions again, but I've slightly reordered it now to show the exact source of the emissions rather than what we get out of it. So instead of cars, I'm talking about petrol engines, diesel engines, instead of aeroplanes, kerosene engines, and so on. Let's imagine what the dream solution would look like in each of these areas. You can see that for transport, what we'd like to do is either to replace combustion engines with electric motors powered by batteries, as we've agreed to do with the road vehicles of the UK, or we'd like to power them with hydrogen, as people are hoping for aeroplanes, or we could power them by biofuel. In the generating electricity, obviously we want to replace combustion-based processes with either renewables or nuclear power, or applying carbon capture and storage to ongoing combustion of fossil fuels, capturing any CO2 before it gets released and making it into a liquid and storing it permanently underground. In industry, then we'd like to be able to power it by non-emitting electricity, perhaps using some hydrogen if that could be made without emissions, and perhaps using carbon capture and storage to control any process emissions that are still released. And in agriculture, we haven't got many options, so we would have to develop and apply negative emissions technologies. And roughly speaking, that picture describes the current solution being discussed in policy internationally. For example, at the COP meeting, these are virtually the only solutions that were mentioned, and in national policy. If you read the UK government's current net zero strategy, this is what it describes. So can that be delivered? If you think about how all of those solutions are developed, then we start by assuming that the final demand for goods and services is untouched. So we come up with a different set of end delivery mechanisms which depend on either a form of fuel or on the supply of electricity or on negative emissions technologies. In turn, the fuels have to be produced and the electricity has to be generated, so there are eventually no emissions. And you can see that all of these solutions depend on just three fundamental resources. That is biomass, non-emitting electricity, and carbon storage. So the key question when we evaluate this idea of the invisible solution based on new technologies is, will we have enough of those three key resources? Well, let's take a look. I've got a graph here where I'm showing on the x-axis the amount of carbon storage that would be required in megatons per year of carbon that has to be captured and stored permanently, probably underground. And on the y-axis, I've got the demand for non-emitting electricity. And the dots here represent a combination of all the solutions I showed on the previous pie chart. How much of those two key resources would I need? And you can see there are many solutions. For example, I could make steel with hydrogen, and I could make the hydrogen from electricity, or I could potentially make the hydrogen using carbon capture and storage. So that gives me two different points on the graph. And if I add up, I could get many, many different dots by combining all the different new technology options. In effect, then, I can populate this graph with a sort of solution space. If I use more biomass, I need less electricity. If I use more negative emissions technologies, I need more. We'll just pause there to talk about biomass. At the moment, averaged over the world, we are eating 100 kilograms of dry biomass per person per year. That is the global average diet. If we just replace the kerosene used to power today's aeroplanes by biokerosene, we would need 200 kilograms of dry biomass per person per year. In other words, we would need to treble the harvest of all current agricultural practice. That is totally impossible to imagine. Therefore, realistically, we should assume that there will be no additional biomass available when we're developing meaningful climate solutions. The question then, of course, is how much of these resources have we currently got? And I've put them on here. You can see that about a third of the world's electricity comes from non-emitting electricity supplies, and there is a little bit of carbon storage, but there's so little that the line hasn't yet left the axis. And this is after 20 years of talking about carbon storage as being a significant contributor to climate policy. Okay, so at the moment it looks very unlikely that we're going to reach this policy space. Let's see how it's growing. Here are the two key graphs. So the first graph shows the history of non-emitting electricity generation in the world since 1965, as it happens over my whole lifespan. And you can see that the graph is fundamentally linear. It isn't an exponential curve like you get when you introduce a new smartphone or a new computer. It's a linear graph, and it grows at a steady rate. And you can see that the line has got slightly steeper since 2010. So we've got an idea of how it's going to grow in the future. If I look at the second graph for carbon capture and storage, that one is also growing. It's growing at the rate of 2 megatons per year every year, so at a relatively small rate. Economists who don't think very carefully about this are confident that if you have the right incentive, those growth rates can increase. But it's never happened before. Look at this history of the introduction of every major new energy source into the world, and you can see that every time, from coal or oil or natural gas or even renewables, then the growth rate, the penetration of the new energy form into the market is linear. And that's because these are big projects. If I look at the way that a new nuclear power station is developed or a new wind farm, then it takes a long time. This is for Hinkley Point C being built in the UK at the moment. If it opens on time, it will have taken 22 years from when it was politically committed to when it starts generating electricity. For the wind farm, it takes 16 years from political commitment to when it's operating. And the reason that that happens is that these aren't just manufacturing problems, they're public projects. They require public finance, they require access to land, they require societal and community engagement. Do people want to have a nuclear power station in their backyard? It needs legal compliance, it needs access, it needs public finance discussions, environmental compliance, and all of these things take time to establish, as well as the fact that they are complicated one-off construction projects. It takes a long time to install new energy infrastructure. And we've looked in great detail at that within our own research group. And you can see that not only does technologies grow in a linear way, but it takes a long time from when they're first invented to when the first commercial installation occurs. After then, there is essentially a linear growth from the first installation to when we get to roughly the peak installation, and the linear growth is not very fast. In contrast, societal changes can occur significantly faster under the right conditions, and that's important when we think about what real solutions might look like. So accepting that growth is going to be linear, or if we're ambitious, twice linear, today's linear rate, we can go back to our graph of resources here and see how the solution space maps to what's available. And you can see that if we're ambitious about the development of non-emitting electricity, we'll get to this purple band here. That's between linear and double linear growth. And however ambitious we are, our amount of carbon storage still won't have left the axis. It's still going to be that small because it's so new, we just can't anticipate it's going to grow at any rate. We don't know how the public are going to respond to it, how its safety implications are going to play out, and so on. So the whole space being discussed in policy, this dream of an invisible solution that the public won't notice, is completely unachievable. There is no possibility that we will have enough non-emitting electricity or enough carbon storage in order to be able to realise this dream of the hidden solution. That's really important. That guides what we need to think about as we look for real climate solutions. Even though it would be easy to deploy because it meets so many acceptability criteria, we just don't have the resources to do it. And yet it's so seductive. Here's a little history of how the UK's Climate Change Committee has advised the government about the future of carbon capture and storage. They keep saying how important it is, and it keeps not happening. But they don't change their mind. They keep saying it's going to be important, and it keeps not happening. Right now, they're continuing to say how important it is, and we might commit to the first demonstrator project in the next few years, but we don't know. We've said that before, and it hasn't happened. It doesn't matter if we have a demonstrator. What matters is the enormous scale shown on these graphs, and it is no longer possible that carbon storage is going to be a significant contributor by 2050. Hydrogen has taken over as the current seductive buzzword, and the UK government's net zero strategy, published just a few months ago, mentioned the word hydrogen 501 times in 360 pages of text, even though, as we stand, there is not a single kilogram of hydrogen being produced in the UK with zero emissions. It looks great, it looks like a conventional fuel, but it takes an enormous amount of energy to make it. Either you need carbon storage, and we don't have any, or you need a lot of spare non-emitting electricity. You can see here just how much additional electricity you need if you're going to power trucks or steel making or homes by hydrogen compared to using an electrical equivalent. So to wrap up, you can see that our pie chart, our petal diagram here of acceptability, it looks as if those technology solutions based on new technologies would work fantastically, but we cannot scale things fast enough. And that means we have to look at other forms of solution which will involve participation from society. It will change the way we live. It does not necessarily mean a miserable life, but it does mean that we'll all be involved in the change, and therefore also that different finance, different economic, different policy and political measures are required to bring about real climate solutions. For now and to date, we've gambled on those new invisible technology solutions. It's a certainty that they won't work. So we have to think now in the remaining films about how we activate a whole wider range of solutions in order to have time between now and 2050 to bring them all into that petal of acceptability.